It's August 2017, and this is episode 77 of the Unseen Podcast, the summer hiatus being over. This is your host, Paul Carr, and with me tonight are Sam Lichtenstein.
Hello from New York.
And Nick Nielsen.
Hello to Paul, and hello to Sam from Portland, Oregon.
And as is our practice, or we practice we're trying to institute, about a month before each episode, we start a discussion thread. And Buckfield, who's not here at the moment, mentioned he wanted to talk about whether math is real, which is kind of I'm not sure that's a well-posed question, but we can talk about that in a moment. But and so if you participate in that discussion, you have an option to be on the panel. And what I would like to start off with is sort of have everybody sort of weigh in on the question of what does it mean that math is real. Now, I want to point out that recently Sam pointed me to a really good essay by a mathematician named Barry Mazur, which is written in very non-mathematical language about
also non-philosophical language. He's quite casual, I would say.
Yeah, no obfuscation, but also not oversimplifying, and in which he talks about his own personal doubts about both sides of the question, and in his own experience as a mathematician, it feels like doing math is a process of discovery rather than invention. Although there are arguments on both sides, and it's a tough nut to crack. It's almost like, what is consciousness, or why be moral, or any of these other tough questions that we humans have come up with that challenge our monkey brains beyond the limit. So let's start with you, Sam. What did you think about this whole topic of, is math real? What does that really mean?
Well, yeah, I don't know how original I can be about this, but I guess intuitively I come down on the side of Mazur, which is, I suppose, on the side of a sort of relatively hardcore form of Platonism, mathematical Platonism, which is the sense that the mathematical entities have some sort of independent ontological existence that is difficult to conceptualize, within a more physicalist or traditional sense of what reality entrains. Now, why do I feel this way? I think basically, Mazur's essay is, I think, a valuable source for this because it encapsulates well the intuition that practicing mathematicians have about this question. An example, I don't remember whether Mazur raises it in the essay, but it's an important one, I think, is something called the yoga of motives. And it's a funny thing, which I don't know whether I'll be able to do justice to in a brief, non-technical description. But roughly speaking, the idea is that various geometrical shapes, geometrical concepts can be described mathematically using a certain algebraic language. And this algebraic language is somehow universal in the sense that it's not at all a priori obviously universal. That is to say that it's not clear based on the initial definitions that the definitions should apply in the context to which they were subsequently applied, sometimes decades after the fact. Rather, people relied upon a certain set of analogies in guiding their intuition about what definitions to make. Those analogies, in turn, reference some sort of what seems to practitioners to be an independent, fundamental mathematical idea that has sufficient independent existence that it can at least guide very clearly how to define further research, like what sets mathematics apart from many other scientific disciplines is that a lot of the work goes into writing the definitions as opposed to describing the objects which fit existing definitions. And so an interesting mathematical statement could perhaps be writing down an interesting definition. And so in this business of the yoga of motives, it's a particularly fruitful area in which merely writing down definitions, following an analogy in a particularly faithful way, has been an extremely fruitful avenue for advancing the discipline. And I think that is quite different from many other branches of science. And it points, from my point of view, towards the idea that mathematics gets towards objects that have independent ontology, insofar as the existential status of the ideas being discussed is bigger than just a social construct. Those ideas exist out in the world as things to be discovered and could potentially be discovered from many different angles. And we approach them as we do as scientists, as humans. But no matter how we happen to approach them, somehow we would approach them nonetheless from whatever perspective we happen to develop. I don't know how coherent that explanation was, but that's sort of my intuition coming from someone with a mathematical training.
Paul, you still awake?
Just checking. I don't know how incoherent I was. Probably quite incoherent.
Paul seems to have frozen up. I see, and I'm getting
That's
a little
right.
bit.
He might be frozen. But what do you think, Nick? What's your reaction to the initial?
Well, my reaction is that I've never heard of the yoga of motives before, so I'm going to have to read up on it. And I started to read the Missouri paper that you sent out, Paul sent out a leak, and it did look like a really interesting paper. I only read the first few paragraphs, and that great quote from Huckleberry Finn that starts it out. Since I've got it here, the paper is Mathematical Platonism and its Opposites, and it starts out saying, quote, "We had the sky up there, all speckled with stars. We used to lay on our backs and look up at them and discuss about whether that was made or only just happened. Jim allowed they was made, but I allowed they happened. I judged it would have took too long to make so many," unquote. So that's from Huckleberry Finn. And then the author of the paper goes on to say how everybody who works in mathematics for a long enough time comes up against the question being whether you're making this stuff or whether you are discovering it. So from my point of view, you come from the point of view of somebody who's had some mathematical training. I'm coming from a pretty explicitly philosophical point of view, and everybody in philosophy basically begins with Plato and Platonism. But even Platonism is usually taken as a very hard form of realism, where you insist upon the independent existence of mathematical objects as having an existential status, and presumably also an existential status distinct from that of mundane objects, which in Platonism weren't ever fully real. We all know the analogy of the allegory of the cave, where the things you see in this world are mere reflections of the eternal and perfect forms. And if you can climb up out of the cave and get into the light of the sun of the good, then you see the forms as they truly are. And that would include the forms that are the basis of mathematics, as well as the good, the true, the beautiful, and that sort of thing. But Platonism itself is not really fully coherent, because it has a lot of elements that have been differently emphasized by different authors. So you find in Plato a very strong denial of the reality of time. There's a beautiful passage where Plato says that time is the moving image of eternity. And there's also the ontological aspect of Platonism. And then there's the metaphysical aspect of Platonism, where mathematical ideas are forms, and the world is really composed of forms, and the world in which we are in is a poor copy of those perfect forms.
Now, it's of course anachronistic, but one could dismiss that criticism with respect to the role of time as a naive one, given what we now know about relativity, right? I mean,
well, there are actually people who interpret relativity in Platonistic terms. There's a guy by the name of Julian Barbour who's written a book called, I can't remember what the heck of the name of it is, something like A World Without Time. Something anyway. The guy's name is Barbour, Barbour. But certainly, since Plato, our whole attitude to science has changed. In the ancient world, science was defined as, starting from first principles, and then you derive from the first principles the truth that you could then go on, and this is corresponded very well to the axiomatic method as it emerged in Euclid, where Euclid was the great synthesizer of ancient geometry and brought together all these theorems into one work and reduced them down to a few assumptions or axioms and postulates.
Right, but to the extent one thinks of that axiomatic work as predicting A from B, predicting consequences from a set of preconditions, it's intrinsically tied up with notions of causality and indeed with our notion of space-time in a way that is quite revolutionized by relativistic physics.
I wouldn't put it that way because I lost my train of thought. Sorry about that.
Anyways, I'm sorry to interrupt, but
no, that's okay. That's okay. I had something I was going to say, but I lost my train of thought. In any case, even though I've thought of myself as a Platonist, more or less, but I don't have much truck with the denial of time Platonism, but the ontological Platonism of assuming the independent existence of mathematical objects. We don't really know. We don't have any good model for what it means to exist if something doesn't exist in space and time. So if you say that mathematical objects exist independently, you end up with, well, does that mean they exist in time, or that they're at some particular place? And of course, almost no Platonist is going to hold that is the case. So unless you're unless you're hold with physicalism, and there are some philosophers who argue for physicalism in the philosophy of mathematics, most people think that the nature of the existence of mathematical objects is something radically distinct from the nature of objects such as tables and chairs and books and things like that. But what it is...
Well, so now you're losing me a little bit, because I'm familiar with physicalism in the context of the philosophy of mind, in which case it's sort of a reductionist philosophy, roughly speaking, the idea that everything reduces to neural signals. And then if one were trying to generalize physicalist philosophy of mind to the philosophy of mathematics, one could imagine there are certain attractors in the space of neural signals or stimulus pathways that are somehow have independent significance. Any mental device, any cognitive machinery similar enough to our own would necessarily gravitate to a certain set of stimulus patterns or brain waves or waves in whatever the cognitive machinery in question is. Maybe there are certain common factors, principal components of thought that are attractors or natural equilibrium states for any it's hard to say any conceivable, but one, in a strong sense, maybe one would say any conceivable theory of mind would end up gravitating towards certain particular patterns of thought, broadly construed.
And that could be considered a sophisticated 21st century version of John Stuart Mill's empiricism in the philosophy of logic and mathematics, and what Frege dismissed as what he called the pebble and biscuits theory of arithmetic. So sure, a good case can be made of it. You could even go farther and say that the kinds of minds that we have, the consciousness that we have, is going to converge on these kind of ideas, that any other pure consciousness would converge on similar ideas. But essentially, mathematics then becomes a cognitive bias. All conscious minds break in this way. Therefore, we've got this discipline of mathematics. And then you get to the problem that Eugene Wigner posed in his famous essay on the unreasonable effectiveness of mathematics and natural science. Why does it work? Why does it work so well? Why was Paul Dirac able to work out the equations and come up with a prediction of antimatter on the basis of mathematical considerations, and then experimental physicists actually did find antimatter. It's almost spooky, you could say, that you can use mathematics in that way. Or the other great example is what was I thinking of a relativistic example of that?
Even just the transit of Mercury, right?
Right. Yeah, you get a mathematical prediction that fits the world just really well, and it seems strange that it could fit the world so well if it doesn't come from some common root. But if we suppose that minds are an emergent complexity from matter, that they obviously they share something with matter, and they do have a common root, even if we don't have a science of consciousness and we can't say ontologically what consciousness is at the present time, we certainly can say, if we're an emergentist, or even if we're a reductionist, we could say that consciousness comes from the same root as the matter of the universe, and therefore it's going to reflect, if you want to call them the same biases or the same realities of being biological. I guess I'm saying is a subset of being material. And so as material beings, we have some participation in the material world.
Right. I guess I'm failing to understand where the challenge to Platonism comes from this perspective.
Well, let me tell you a strange story. I don't know if this has any relevance because it's personal anecdote. But having been, like I said, more or less a philosophical Platonist for most of my life, there was a story a few years ago where, you know how crop circles turn up from time to time, and some people think that they're made by aliens who come down here to stomp on people's cornfields. But there's a crop circle that appeared a few years ago that was the most famous image of the Mandelbrot set. And as soon as I saw that, have you seen a picture of that?
I have not, but I know I can visualize it in my mind because I've seen the famous.
So there was a crop circle of the Mandelbrot set, and as soon as I saw that, I had a visceral reaction to that I did not expect, which was my visceral reaction to that. How would anybody think that this was anything other than human? Which implies to me that my visceral reaction was the Mandelbrot set was a human invention that came at a particular point in history and has a whole antecedent that comes up to it. You could give it a Platonistic interpretation too. You could say, that any...
I would say that's a deeply cynical reaction upon your part.
Well, yeah, I suppose I can be deeply cynical at times. But it was a visceral reaction. It was a genuine reaction, unmediated by any...
I can even sympathize, to be honest. But, right. Yes, right. So that intuition that you're getting at is the idea that, yes, we humans have a very contingent history in our understanding of mathematical ideas, which leads us to things such as the Mandelbrot set as we think about it conventionally. And so it seems preposterous to imagine that when encountering such a phenomenon in abstracto, supposedly, such as in this example of a crop circle, that we would happen to encounter upon something so accordant with our own contingent sociological construct of the same mathematical idea.
And at the same time, because if the crop circle of the Mandelbrot set had appeared 200 years ago, or say just when photography was getting going,
it would be completely meaningless to humans. That's right.
Right, yes. But if it was, you took a picture of it, or somebody painted a picture of it, and then that survived, just like in the movie 12 Monkeys, where they've got these pictures from World War I and Bruce Willis is in it. If it survives into the present at a time when you can actually interpret what it is, then you think, oh wow, that's really spooky. That's more spooky than Paul Dirac deriving the existence of antimatter. That would be
right. But you actually have to have enough conversance with the Fermi, the Dirac, the Fermi paradox or whatever, the Drake equation, in order to understand just how contingent such things are, right? To appreciate the degree to which those accidents of history and timing make a difference in terms of interpreting the significance of what you observe. I agree with that. That's an important point, actually, I think.
The other big challenge to Platonistic thought is the rise and the growth of explicitly constructivistic thought, which almost perfectly coincides with the emergence of computing as a science in and of its own right. So you get Turing and Church laying down the basic ideas of a universal computing instrument, and you've got the rapid growth of recursive function theory and the related aspects, and now computer science is a big booming industry, and computers are central to the economy.
And indeed, computer-assisted proof in mathematics is
yes, yeah. But computers can't do.
But just to anticipate what you're going to say, why exactly do you feel this is in tension with Platonist?
Because computers are essentially an embodied decision procedure, and an embodied decision procedure is always going to be finitistic and is always going to be essentially constructivistic, and you can't get a computer. I can't say can't. There probably are workarounds where you could get impredicative reasoning or infinitistic reasoning or use of the tertium non datur in infinitistic contexts, which is particularly problematic, and which is why the intuitionists since Brouwer have rejected tertium non datur, the law of the excluded middle, that is P or not P, either P is true or P is not true. Which in ordinary finite cases it's not a problem, but when you put it in an infinite context, then it generates all kinds of paradoxes.
But couldn't you imagine some sort of I think if I might be misinterpreting you, but if I'm understanding correctly, you're saying you believe there might be potential philosophical ontological contradictions that arise, in particular with the infinitary aspects of mathematics. And
there's a whole industry of people who produce contradictions and paradoxes.
It seems perfectly reasonable to me to believe that there could be compromised positions whereby one could believe that mathematical objects exist independently in some infinitely accurate approximation of whatever infinitary abstraction one believes is some sort of mathematical ideal that individual mathematical reasoners aspire towards or work in relative towards. Like individual mathematicians might conceptualize their thought with respect to an ontology that requires philosophical assumptions that are not borne out, but could nonetheless be consistent with an actual existence of mathematical objects that don't demand such rigorous infinitary assumptions, if you will.
Yeah, that I think that's absolutely true. And in fact, a couple of years ago, I was corresponding with a guy who was homotopy type theory is one of the big deals in. Well, I consider it constructivistic. I don't know if the advocates of it consider it constructivistic. Anyway,
Vladimir Voevodsky, he's a Fields medalist. He's working very deeply on this at the moment.
Yes, and I think Carnegie Mellon got a grant of like $10 million or something from the Defense Department to work on it because it might be useful for cryptography or other advanced communication technology.
I'm somewhat skeptical of that, but yes, I agree that there's been funding towards this effort.
Yeah, there has been funding. Okay, we've got a philosophy, essentially a foundationalist philosophy of mathematics that's gotten government funding. I think that's great. I'd like to see more foundations of mathematics people get huge government grants so they could do more work.
I can get on board with that. Yeah, I agree.
So anyway, I was corresponding with this guy about homotopy type theory, and he said that it doesn't incorporate any assumptions of domain finitude. So some of these practices, they don't stipulate, they don't have any, they don't force you to think finitistically, but at the same time, they don't push you out toward infinitistic reasoning at the same time, because that's just not what they're doing, and that's not what the mechanisms are like. It's
that's a feature, not a bug, from their point of view, probably.
Yeah, from their point of view, it's a feature. It's a feature, not a bug. What was the other thing I was going to say about finitism? Oh, well, all the compromises that are in place from the point of view of mathematical practices. I think we said something about that recently, which is known as the philosophy of mathematical practices is sometimes called neo-empiricism. I think Philip Kitcher was the guy who came up with that, but I'm not sure.
I think I've read his book. Yeah.
The Nature of Mathematics. That's off the top of my head, so I'm not sure about that. Anyway, the whole story of the axiomatization of set theory from Zermelo to the present day is a series of compromises with the attempt to maintain what Hilbert called Cantor's paradise, this realm of transfinite numbers as a pure area of mathematical research, to reconcile that with finitistic methods like axiomatics. So you have, the Zermelo-Fraenkel set theory has the axiom of foundation, which requires that every membership chain has to ultimately come down to membership in a particular set. So in other words, you can't have an infinitely descending or an infinitely ascending membership chain. And that prevents you from formulating paradoxes like Russell's paradox. And once you know what Russell's paradox is, which is a set of all sets which are not members of themselves, once you know what that is, you can basically use it as a template to generate paradoxes and contradictions in almost any branch of mathematics that uses strong set theoretic level assumptions.
Yeah, and I would say, by the way, that Hilbert's intuitions about this area are one of the most successful mathematical theories, if you want to call it a theory, of all time. Hilbert,
it depends on how you. I don't think many people interpret it that way, because many people interpret Hilbert's program as having been utterly defeated by Gödel's incompleteness.
I'm aware of that, but I think that's empirically false. And so here's my point: is that Hilbert more or less intuited a set of essentially reasonable assumptions that you should make about a practically feasible set of mathematical axioms, which allow you to do math as it actually affects the real world, as mathematicians actually care about it, without running into contradictions. And he's been completely vindicated in that set of axioms. I'm not aware of any sense in which there's been any remote degree of tension between sort of, there was a bit of action around the continuum hypothesis in the 50s and 60s when Paul Cohen or whoever was.
Yeah, Cohen came up with forcing, which proved that the continuum hypothesis is independent from the ZFC the ZF axioms. The ZFF, Zermelo-Fraenkel Skolem axiom set, which is multiply revised.
That is the closest anyone has ever come between, to finding a genuine tension between these issues of infinitary mathematics that arise when you really sort of delve into the deep foundational questions and mathematics as it concerns the real world. I don't believe that there are, and when I say the real world, I mean the real mathematical world encompassing Platonistic domains whose existence we might not even acknowledge as part of this discussion. But working mathematicians, as a rule, did not encounter foundational questions as a salient issue, philosophical or practical in their work.
Unless that's their specific field of research. Yes, that's largely true.
And I think that's quite interesting. And the fact that it was not difficult for Hilbert to pin down what set of assumptions are required to essentially rule out these foundational questions strikes me as itself a statement of some foundational consequence. Maybe I'm.
Do you know what's written on Hilbert's tombstone?
I do not.
We will know. We must know.
That's right. I'd say we don't know, but we still must know.
Yeah. I guess you could take that in a modal sense of we did know, or we can know, or we will know. But have you ever read Hilbert's essay on axiomatic thought, axiomatische Denken?
It doesn't come to mind at the moment, possibly, but I don't think so.
It's a nice little essay, but when I read that, it really struck me. Obviously Hilbert is one of the most famous mathematicians of all time. But from my philosophical perspective of reading Hilbert's essay, first time I read it, I thought, this guy is not an abstract thinker. This is just, it's all nuts and bolts mathematics, and it's not.
He was relatively close to physics in his research. He did it.
And Hilbert was more or less in a race with Einstein to come up with the equations of general relativity, because everybody could see what was coming at the time, 1913, 1914, up until, Einstein got them out himself first, but Hilbert was working on the same problem. So yeah, his work was deeply related to physical theory and deeply applicable, and that's probably not only sufficient for most mathematicians, but that's pretty much what most mathematicians are going to be interested in. But a philosopher coming to mathematics is going to cherry pick the most interesting ideas. And those ideas are going to be like, set theory and transfinite numbers and bizarre kinds of geometry that can't be intuited by a mind conditioned to 3 dimensions and stuff like that. So I guess it's like it's sort of like the difference in conceiving of history. Stephen Jay Gould liked to say that history is dominated by microorganisms, always has been, it is in the present day, and then we're just a little tiny bit of the long tail of life. Whereas, so this really de-emphasizes the role of humanity and intelligence in the history of life. But then you have the people in big history, and they view, they acknowledge that this is the bulk of life, but the other stuff, you focus on the emergent complexities, and the emergent complexities is, for all we know, just a few things happening on Earth, and we don't know if it's happening anywhere else, but that comes to dominate the foreground, even if the background is the bulk of life. So it's the philosophical attitude from my point of view, which is probably not shared by a lot of other people, is you're going to go for the emergent complexities in mathematics, and yes, the background is all this other stuff. But perhaps the mathematical viewpoint is all that other stuff is the real mathematics, and these emergent complexities from math aren't necessarily to the point. They're curiosities.
Off the top of my head, that sounds correct. It's just the question that, as somebody who knows a little bit about math, it makes me question the intuition of people when they attempt to adjudicate what the sort of the fundamental things that are left over. So as you mentioned, for example, in terms of astrobiology, like this idea that we can abstract away to what the fundamental philosophy of life, whatever you want to call that is, like we have certain intuitions based on our own experience, and basically the intuitions of philosophers of mathematics with respect to which intuitions are important as regards the philosophy of mathematics makes me question whether we as humans have accurate intuitions with regards to which intuitions are important when it comes to the philosophy of life. Does that make any sense?
Yes, it does. And
you emphasize certain things based on our experience, which may or may not be accurate. And since we're so limited in what we've experienced, it's very difficult to critique any particular view about what is accurate or not.
Interestingly, we don't need to have a definition of life in order to do biology. And astrobiology builds on biology, so you don't even need a definition of life. You don't have to say this is the essence of life in order to do astrobiology. I view astrobiology as essentially expanding the scope of biology. So instead of just focusing on what macromolecules are doing here on the surface of Earth, you're focusing on their whole history and everything that brought them about and where those conditions can be found elsewhere in the universe. So it's an expansion of the scope of biology, which still doesn't require a definition of life. And in the same way, perhaps.
But here's the point I'm trying to make, though, and maybe you disagree, is that in expanding the scope in this way, one necessarily appeals to intuition in certain degrees, and such appeals to intuition could be fundamentally misguided.
Yes, I agree. Those could be fundamentally misguided. They also could be, at the same time, fundamentally human. The question is, what does breaking human mean? Is that basically deviant from a point of what would be an ideal pure rationality, or are we just imperfectly trying to grasp that Platonic form that's out there and just out of our reach? But the inability to define life for biology, which is not necessarily a view that everyone shares. Of course, Schrödinger thought that it was essential to define life. Interestingly, corresponds to Hilbert's famous conception of axiomatics, because he said the point, line, and plane could be replaced with table, chair, and beer mug, and you still get the same formal results. I mean, you get a syntactical derivation that's still valid regardless of the values that you give for your variables. And there's also a great quote from Bertrand Russell, that mathematics is the science in which you never know what you're talking about, nor whether what you are saying is true, which is deeply embedded in the hypothetical deductive paradigm, as is Hilbert's thought. So even though, despite the differences between Russell and Hilbert, they were both very much working in this paradigm.
I have to imagine that both of them were sort of very much within the intellectual paradigm of their era. Hilbert was thinking explicitly about the fact that there are multiple models for any given theory, to be sort of somewhat technical about it. And, who was the other person you cited?
I was mentioning Russell and Hilbert.
Russell and Hilbert, yeah. They were both probably thinking about this fact that, like, any particular theory that you write down, set of axioms which imply, given a set of derivation rules, a certain set of theorems, it implies a set of propositions, and those propositions are valid in the context within which they are valid, essentially, and that context is all important in terms of interpreting the significance of the derivations in question. But
yeah, they both, Hilbert representing formalism, Russell representing logicism, and Brouwer and Heiting representing intuitionism were all early foundationalists who were deeply involved in laying the foundations of mathematical logic, which has now gone on to become a discipline that's independent both of logic and of mathematics, for that matter, and foundations of mathematics too. And they were all focused on the question of the relation of logic to mathematics, and they had different theses that they held on these things. But that was the question that set the agenda today, and it's not the question that's setting the agenda today.
Well, it's interesting contextualizing that with respect to the agendas today, right? So the agendas today is set by a combination of two things. One is mathematics as qua mathematics, which has its own independent motivations. There are various questions that mathematicians view as interesting. And in some cases, so you mentioned Voevodsky's work on the homotopy type theory, there are actually interesting interactions between these sort of foundational issues and sort of more what conventional mathematicians would consider fundamentally important mathematical questions. And on the other hand, you also have people interested in things like computer-assisted proofs who are working somewhat more directly but using quite related techniques towards applying a more Hilbertian vision of mathematics to practical mathematical research. And they're achieving ever more important insights. For example, a very interesting example of the sort of problem where this is interesting is Kepler's problem, which is about finding dense packings of spheres in spaces, say three-dimensional space, for example. I believe this was a relatively recent achievement, last few years. Roughly speaking, if you're trying to pack oranges as densely as possible, there's an obvious way to pack them. But can you prove that's the densest possible way to pack oranges? If you have
Right.
like a shipping container, you want to pack as many oranges as possible, you'll try to pack them in the obvious way, which is a kind of what's called a hexagonal something or other packing.
Right.
Basically, you put the each new orange into the gap where the previous layer of oranges is lying. It's a very intuitive packing, but is that really the best? And that's a computational question, as we understand it today. It's not we have some sort of theoretical understanding, but
and it becomes an even more difficult nut to pack in higher dimensions, because there are people who study sphere packing in 4 or 5 and higher.
Vastly more interesting in higher dimensions, in fact, yes, and highly relevant to important areas related to signals processing, error correcting codes, internet protocol, blah blah blah. It's a very important question, in fact, in higher dimensions. But these are questions that we currently approach in a computational manner, and the question of whether we can prove our answer is correct is subtle and difficult at the moment, at this current moment in time. And I just think that's interesting because it's quite different from any previous moment in mathematical history, as far as I'm aware, insofar as there are questions that we can answer by a computer and not by a human, and in no other way.
And the question then becomes, can a human being check the proof that's so large that can only be come up with by a computer?
That's correct. That's extremely
and whether,
yes.
Does a mathematical result have to be appreciated by a conscious mind in order for it to be a valid mathematical result? So if a computer proves it and says it's proved, and everybody can avow that, the engineer can say, yes, the computer is working fine. Is that a mathematical theorem, or does it have to be understood by a human mathematician to make it, or some other biological mathematician?
And I would suggest that almost all mathematicians, and probably almost all computer scientists, and probably almost all working software engineers, probably say no. The human consciousness plays absolutely no role in this process. It's an independent reality.
Well, which is Platonism once again. So you get Platonism emerging from the intrinsic constructivism of finitistic computational thought.
Yeah, and I think somehow this intuition emerges quite naturally from a variety of perspectives. That's not to say it's correct necessarily, but I think it is somehow very attractive from a variety of points of view.
But if we look back to the in the end of the 19th century, beginning of the 20th century, the process of the arithmetization of analysis, which was an important driver in the emergence of mathematical logic, and it really influenced the people who worked in the foundations of mathematics, like Russell, Hilbert, and Brouwer, who we mentioned earlier. There are a lot of, up until the limit method was used in the calculus, and it was basically based on geometrical intuitions, and then people like Weierstrass worked out a way you could do it with, and then of course the Dedekind and the Dedekind cut,
roughly speaking, yes.
Right, to do this with arithmetical means rather than geometrical means, and it greatly increased the rigor of the calculus and its application. And a lot of theorems that had been used for many years ended up being tossed out, like Taylor's theorem, and and then you got the response of groups like the Bourbaki group in France, which wanted to really double down on the rigor in mathematics and set things straight, because things
just to interrupt you briefly, one very interesting point to make is that those theorems may have been tossed out, but none of them were repudiated.
Good point.
Subsequently reproved as essentially correct statements.
Yeah, reproved by constructivist means.
With more precise conditions.
You can't do physics without Taylor's theorem.
That's basically right. I think Paul's correct. Like, essentially, the pre-rigorous school of calculus, roughly speaking, arrived at all the correct conclusions. And whether that was driven by physical requirements, which I think is probably historically the important driver of what was going on, or other more philosophical considerations, which may or may not have been important, they got the right answer despite using mathematically unfounded methods. And that's at least worth pausing upon and thinking about a little bit, I think.
It is worth thinking about, because that we're seeing a parallel later development now, where constructivist mathematicians using explicitly constructivist methods are going back and trying to reprove theorems that were only proved by non-constructive means, because all of these are now viewed as suspect in the current constructivist climate. That's
Nick, can you give the explain Lecon 5 definition of constructivist?
Well, I like the simplest way to make the distinction, but the most intuitive way, is to say that constructivism is proceeding from the bottom up, and non-constructive things are looking from the top down.
No, that's the one. Explain like I'm 15. I want explain like I'm 5.
Okay. The best illustration I've gotten of this is from a book by a French mathematician. I can't remember his Alain Connes, Connes. He said that the constructivist is like the person who climbs a mountain, the builder, the boulderer who goes up a mountain bit by bit and finally gets to the top by clambering over it. The non-constructivist gets in a helicopter and flies, and it gets dropped down on the top of the mountain. So the non-constructive perspective is this: you cut the Gordian knot, you make the deduction on a general principle, and you apply it downwards, and you see the mountain from the top down, but you don't see the details. The constructivist is starting from the bottom, from the foothills of the mountain, and going up to the top. But that's the intuitive picture you get. There is, as far as I'm aware, and I've worked on this problem for several years, there's no one intuitive constructivist intuition that lies at the base of all the different forms of constructivism, because there are constructivists like the intuitionists and started with Brouwer, who rejected the law of the excluded middle. And so intuitionist mathematics makes use of logical principles that exclude, not including the law of the excluded middle. In intuitionist mathematics, double negation does not equal the affirmation of a proposition. But then, that's only one species of constructivism. You can also have the constructivism that comes from avoiding the vicious circle principle and impredicative reasoning.
I can shed a little bit of intuitive light onto this question. It's not going to speak directly to the subtleties that Nick was worrying about, but a very famous example of constructivism is the question of the rationality of the square root of 2. So the square root of 2 is not a rational number. One can prove this relatively easily by contradiction. So if you assume that there's some rational number a over b, whose square is equal to 2, then via parity considerations, roughly speaking, like whether numbers are even or odd, you can come up with a proof by contradiction that there's no reduced form fraction a over b, which is the simplest fraction, such that a over b squared equals 2.
Right, okay.
All right? That is a non-constructivist proof, because you don't actually construct a fraction. Essentially, contradiction. You're not producing anything that violates the square root of 2-ness of rational numbers. On the other hand, there's also a constructive proof of the same proposition. The constructive proof requires showing that for any particular rational number whose square is relatively close to 2, it has to satisfy certain hypotheses, which are impossible. So roughly speaking, it's the difference between showing the non-existence of an arbitrarily good rational approximation to the square root of 2, not arbitrarily good, but good enough that it could actually be a true rational number, versus an infinitary impossibility proof that there could be a square root of 2 that is a rational number. Now that I say it, it's less obvious. It's a less clear distinction there.
I was pretty happy with the reductio ad absurdum argument, right?
But reductio ad absurdum is a non-constructive proof.
Yeah, but
That's right.
Why does anybody have a problem with that?
Well, because in an infinitistic in an infinitistic context, it creates contradictions.
Reductio absurdum implies saying, if you give me a contradiction, I can produce for you a contradiction. So you're giving me leeway to use whatever tools I have at my disposal to produce a contradiction. And so you can start worrying about what tools I'm using. And when my tools start including sort of shifty things like the axiom of choice or things that involve infinities in very subtle ways, you can start worrying about whether I'm playing tricks on you when I'm producing the contradiction. I think that's probably a roughly correct way to think about where the issue arises.
Because when mathematical logic started out, nobody knew it was going to result in contradictions like Russell's set, the set of all sets that are not members of themselves. But once you start down this path of set theoretical reasoning, you run into this contradiction. You run into it repeatedly, so you have to restrict your reasoning in one way or another. And the whole question now is, how do we restrict our reasoning and we still allow ourselves the things we want to do with mathematics? And that's not yet evident more than 100 years later.
But the miracle is that, like, for certain restrictive sets of things you can do, you never run into contradictions. If you restrict yourself to, like, normal things, roughly speaking, if you avoid infinities, you're basically fine. Math works okay. I'm confident the math is correct.
You're confident, but can you prove it with anything other than a relative consistency proof?
Correct. I cannot. And that's intuitionistic mathematics has no contradictions in it so far. It's pristine so far as we know. And maybe people can continue to reason that way for another 1,000 years and never run into anything, but we don't actually have a proof that that's the case. There may be relative consistency proofs that reduce the consistency of constructivistic or intuitionistic mathematics to some other theory assumed to be consistent. But even then, that begs the question, because you have to have an original theory, like, say, Euclidean geometry as your basis for your relative consistency proof. And so, you can then appeal to empirical questions. Does
it work?
Right. It's been 2,000 years since, Euclidean geometry was discovered as a mathematical system of axioms. And no one has discovered an inconsistency. So, that's a pretty good empirical evidence, as an inductive reasoner, to believe that it's free from contradictions, And
similarly with constructivistic thought today, it seems to be pretty good so far, and people can, build bridges with it. But then again, people built bridges with classical mathematics for thousands of years, and but that was before we actually systematically applied science and mathematics to the construction of
and now we have computers who can automate the attempt to find flaws.
Yes, and you could push your axiom systems out arbitrarily much faster than human beings can push them out. So you'd have an enormous amount of inductive proof for the robustness and consistency of your system of mathematical thought. But
it's actually sort of less obvious than one might think, insofar as, like, computational complexity reasons now allow us to push into regions of what I believe is technically called Kolmogorov complexity. Complexity.
Yeah.
Roughly speaking, the complexity of a statement being the length of the string it takes to state the statement. The number of bits you need to express a theorem.
Yeah, the algorithm that you need to create the statement, right?
Right.
Yeah.
And so we're now able to push that out into ways that are actually historically completely unprecedented. And so how confident we should actually be in our beliefs in what the domains of Kolmogorov complexity that we've explored, given our historical evidence for what we know, what we've seen empirically, it's sort of an open question. I'm not sure what the philosophical approach to this question is. As a Bayesian, my Bayesian approach would be to say that we can probably generalize pretty well to domains of complexity pretty far beyond what we've experienced in practice. But it's not really clear to me what the right priors are to use in terms of coming up with degrees of confidence about this sort of question.
Yeah, well, knowing what the priors are is always the trick with the problem with Bayesianism, right? You don't always have a good way to establish those. So you guess and then you keep updating.
Yeah, you keep guessing, and
which is in engineering, by the way, works marvelously well.
Yeah, it's never really been a problem as far as I know.
You figure out what a good guess is, and then you update the guess.
Are there famous examples in engineering where like a well-established, totally trusted approximation regime just totally broke down once you got to a new level of skill?
That algorithm that was designed to play the markets and be completely undefeatable, that failed catastrophically. I can't remember the name of it, but it was a few years ago, in the early 2000s, that these people came up with an algorithm they thought that was going to be able to play the market so well that whether the market was going up or down, you're still going to be making money. And when the financial,
I suspect it was not thought by anybody who'd actually played the markets.
I could find the reference to it, but I can't remember the name of it off the top of my head.
Oh, you mean the orangutan with a dart? Orangutans are pretty clever,
Before we close down for the night, we'd originally planned to sort of pivot this towards MEDI.
Yeah,
so I thought I was coming to a MEDI discussion. Yeah,
but you guys were getting so abstract. I figured we'd have no listeners at all. Then we can. Yeah, they're gone now. Now we can talk about MEDI.
We can talk about MEDI. I'm happy to talk about MEDI, even if we've lost all our listeners.
Well, I mean, the question with MEDI is right. Is the human construction of mathematics? Is there anything about it that we could reasonably expect to be universal for other biologically involved organisms in comparable environments to understand?
So here's why I raised this in the context of this conversation. And this is because there's a specific thing I know about in math called the classification of finite semi-simple Lie algebras. This is a thing. It's a thing in math. It's sort of abstract, sort of advanced. But it ultimately boils down to there being a certain set of combinations of angles that are special. And these angles are like, if you have a certain set of directions in n-dimensional space, and some directions are at right angles to one another, and some directions are at 60-degree angles to one another, those combinations work out well. And you end up generating a set of sort of symmetries that are special. If you take a random set of angles in n-dimensional space, let's say, for example, think about two or three dimensional space. If you pick a random set of angles, and then you do all possible reflections across those angles, you're going to get an infinite set of possible reflections. But for a very specific set of angles, 90 degrees, 360 degrees, 120 degrees, you'll see special phenomena arise. You'll get a finite set of possible angles that arise, finite set of symmetries, reflections.
Mm-hmm.
The same thing holds in higher dimensions. And we can completely characterize in all possible dimensions all the possibilities of how you get a finite set of symmetries from a fixed finite set of initial reflections. And certain dimensions are special. For example, 8 dimensions is special. 24 dimensions is special. This is why you get these news articles about special physical theories belonging to 24 dimensions or 8 dimensions. There are certain mathematical laws that explain why you get extra symmetry given a certain number of dimensions. And this seems to me I have this very deep intuition that this is the type of mathematical discovery, and I say discovery, not invention, that is so deep. It just has to be true. It's a property of space as we think about it, not a property of our particular perception of reality, that any sentient civilization would have to be aware of this on some level if they're of the sufficient technological status that we could conceivably communicate with them. So this is where mathematical Platonism gets meat for me. It's there are certain mathematical theories whose connection with both physics, our current best understanding of physics, and seems so fundamentally tied to, I guess, the geometry of the space-time in which we live, that it seems inescapable that it has its own independent reality. And I'm aware that I think this reality could be completely illusory, and yet it's almost inescapable for me. This relates to the essay that Paul mentioned earlier by Mazur. People who spend the time to learn about advanced math almost universally come towards this sort of point of view. And that seems like an informative data point, whether or not it's dispositive towards the ultimate philosophical question of mathematical ontology.
Okay, but how do we transmit such an understanding? How would you encode it?
Oh, well, that's part of what's interesting about it, is that what in the 19th century, when this stuff was being worked out for the first time by Sophus Lee, I think he was Swedish, some Scandinavian guy. He was the guy who first figured this stuff out. He had a student, a Russian mathematician named Dinkin. He was like, nowadays we have these things called research opportunities for undergraduates, which is where like a professor will invite an undergrad to work with them for a summer as a way to get training towards being a researcher in the future. So in like the 1920s or so, this guy Lee invited this Russian guy Dinkin to do one of these, essentially an undergraduate research project. And his undergraduate project was to, think about these symmetries and come up with a way to characterize them in a way that's like easily explainable or like easy to classify. And what he came up with, what was called the Dinkin diagram classification. You can classify the fundamental building blocks of symmetry, or sort of, you might call them finitary symmetries. They're the symmetries that build up the irreducible. It's fair to say they're like the irreducible building blocks of symmetries, of continuous symmetries in the universe. I think that's a relatively reasonable characterization of what they mean mathematically. Technically, it's the classification of irreducible semi-simple Lie algebras. So this Russian undergraduate, Dinkin, figured out that there's a one-to-one mapping between these mathematical objects and certain kind of diagrams that you can draw. The diagrams that you draw are just like a certain set of lines. They're just like dots and lines. And the lines correspond to 90-degree angles. And you can draw a double line if it corresponds to a 120-degree angle, or a triple line if it's a 145-degree angle. But like, roughly speaking, they're just combinations of vectors and angles. And it's a completely algorithmic classification of what combinations work and what combinations don't. He encoded it all in this very simple diagram language, which would be very easy to write, for example, on the Voyager tablet, record, whatever. It's not a large number of bits to communicate to an extraterrestrial civilization.
Do you think the space, the area available on the space probe would be better spent communicating these Lie group symmetries than having the record or the picture of the two people in the Pioneer plaque?
Yes, I actually say yes. No doubt to me. There's no question to me that's a better thing to do. Yes.
I think it would be helpful to make a distinction between mathematical ideas that are tightly coupled to advances in science and technology, and mathematical ideas that are not tightly coupled. Because if you get a civilization that's gotten to the point where it can formulate those what is it, Maxwell or Hertz, who wrote Maxwell's equations that account for electromagnetism. You pretty much have to reach that level of mathematical sophistication to build a radio telescope or to build electromagnetic devices that would communicate.
Yeah, that's an interesting point, because empirically, we definitely did not reach that degree of mathematical sophistication before reaching the appropriate degree of technological sophistication.
Because they were driving each other. By the time
possibly, but we were definitely exploiting the technology decades.
Well, no, I don't think so.
Multiple decades before
we didn't have radio before we had Maxwell's equations.
The point is, I don't think we were not mathematically cognizant of the fundamental symmetries I'm talking about here. It was at least 20 to 50 years before. Like, we understood the physics and we understood the engineering, how to do radio, say 20 to 50 years before we actually understood the math of how this stuff worked.
Well, we had other law. Part of what Maxwell's equations did was he took things like Faraday's law and D'Alembert's law and unified them into a single system with the right math. But yeah, we knew what induction was.
From our modern point of view, it was not the right math. We had a shitty version of the math. We had some sort of crude, practical version of the math. And nowadays we have a much better, cleaner version of the math, which reveals what I think of as the fundamental mathematical truths, but was emphatically not at all required for the original practitioners to produce the initial technological demonstrations.
So you can have a rough mathematics that gives you a rough technological capability, but it takes longer to evolve to arrive at those better expressions. Well, I think what Erdos called proofs from the book, the definitive.
Yes. That's exactly right. Yes. Yeah. We had the technology demonstration many decades before we had the proofs from the book.
So, but what I'm trying to get at is not in all cases, but in some cases, there can be a separability between the mathematical achievement and the technological achievement. One of my favorite examples of this is the Greeks worked out conic sections out of a pure love for geometry. And you can still read, what was it, Apollonius, who wrote the book on conic sections. It's an incredible piece of work, and it's so abstract for its time, has no applicability until during the Renaissance, when people discovered that projectiles actually followed a course that could be described by a conic section. So suddenly conic sections became important for military artillery, and people started studying it for practical reason. But it wasn't developed for practical reason. It was developed completely on one side out of pure love of mathematics, and it sat around for 1,000 years before it had any utility. And we could imagine the opposite case, where a technology might be invented and used for 1,000 years, and nobody might understand it and come up with the mathematical basis of it or the scientific basis of it for 1,000 years. But not in all cases. In some cases, like I'm saying, I think it's very tightly coupled. You have to do a really good radio telescope or a transmitter that could transmit over interstellar distances. You have to have a certain minimum threshold of mathematical sophistication. And it doesn't necessarily flow over into things like that Sam was describing in these symmetry groups, or doesn't necessarily include foundations of mathematics and set theory, but it's still a pretty sophisticated mathematics.
Yeah, I mean, you could build a waveguide without Maxwell's equations.
Or a GPS satellite, Like, you have to understand Einstein's equations.
Yeah. To do GPS right, you have to have the general relativity, because it has to correct itself all the time.
Not only that, but the GPS satellite uses a phased array, which requires Maxwell's equations to get it right.
Sure, but even just discussing the more mathematically advanced aspects of Riemannian geometry, that's how we conceptualize it, at least, you know.
So in terms of another species emergent on some other world, some light years away, that we could only communicate right at our present technological level by radio, to what extent can we set the parameters of its intellectual development? And we can't say that it's going to build a radio telescope without understanding these symmetry groups, or it's going to understand these symmetry groups but not yet have arrived at the point of building a radio telescope. So how much can we contain this discussion in terms of...
It might have understand the symmetry groups, but would it have Dinkin diagrams? That's what I want to know.
That's I think sort of the interesting question is, could you understand the symmetry groups without developing the Dinkin diagrams?
Can you understand quantum theory without Feynman diagrams? Does anybody understand?
Yeah, you do actually. They have there are people doing quantum field theory now without them and making good progress.
With respect to the philosophy of mathematics, I think that's exactly the question that's under discussion here. Is we have models for thinking about more advanced scientific theories in ways that we can think about more easily, perhaps contingently, but to what extent and they have the property that they reduce potentially high dimensional, high complexity problems into a lower dimensional, lower complexity realm of conceptualization. And that's helpful for us. To what extent is that fundamental to the nature of science as crosses species boundaries, right? I mean, like, I think that's part of the fundamental question at issue there. Right?
A very different being emerging and evolving under very different circumstances, but it does evolve in abstract intelligence. You know, what order is it going to discover these mathematical truths? Is it in any way tied to the order in which we discovered them, or might they have discovered the lead groups first?
I can tell you my intuition is that it seems extremely unlikely to me that the order in which they discover stuff is completely uncorrelated from the order in which we discover stuff.
Not uncorrelated, but it's going to be, whereas I think our mathematical development is tightly correlated to our...
I agree that it's different, but like,
right,
it's not in the opposite order, right? Like, there's clearly some order. You know, if you plot the order that they discover stuff in and the order that we discover stuff in, there's going to be some correlation between those two things based on a hierarchy of complexity of ideas. And that's not an intrinsically inaccessible thing for us to understand.
That's right. But civilizations could take a very different route of development because some ideas that are not especially difficult appeared relatively late in human civilization. So, for example, something I have written about, but I don't think I put it on my blogs or anything, is the idea of natural selection is pretty easy to figure out. Once you've been told it, it's easy to understand. It's easy to interpret the biology of the world in terms of it. Say that instead of Euclid in the ancient world and the development of mathematics and Greek civilization, biology was the focus rather than geometry. And we grew this somebody wrote The Origin of Species in 250 BC, and we had 2,000 years worth of civilization with advanced biological knowledge, but nobody actually stumbled upon the systematization of geometry until, say, 1859. So, you could get, some very different, results from those different orders of discovery.
Yeah, you could.
That's an interesting thought experiment. But so what conclusion do you draw?
Well, that the mathematical and scientific development is going to be largely correlated with the socioeconomic development. And like I said, I think there's going to be tightly coupled correlations and loosely coupled correlations. So, like I said, you have to have some kind of ordinary counting numbers before you can do more advanced mathematics that are based on simple tallying numbers. But then that's a very loose correlation. But there's going to be more tightly coupled correlations, like having to have a sophisticated theory of electricity in order to build a sophisticated electronic device, like we talked about GPS satellites and stuff like that.
Mm-hmm.
But to try to tie this back to the METI thing, since we haven't actually touched on METI, we've talked about commonalities of other species or the lack of them. One way to I'm not saying that everybody would accept this, but one way to get around the METI debate would be to say, transmit on something that could only be understood by a sufficiently sophisticated civilization, and both in terms of the signal employed and the information encoded. So you limited your METI transmission only to a certain class of intelligent beings who presumably would have enough in common with you scientifically that they would not want to come here and take your home world and extirpate all the members of your species. Now, why that would follow from mathematics, I admit I don't have an argument for that.
Well, the signal format can be pretty simple. I don't think that's really controversial. I mean, just continue. Ham radio operators are doing the same thing for generations, right? You just turn the transmitter on and off to encode 1 0. That's called CW, and you would expect that anybody who'd mastered microwaves would understand that was a code.
But did either of you listen to the interview with Snowden some months back, or maybe last year or more, when he talked about some SETI issues?
No, I mean,
it was just a short part of an interview, but he talked about and I didn't listen to it recently, so I can't pull this out exactly, but it was like SETI that would be virtually indistinguishable from the background noise. That's what I mean by encoding it. You could send a very obvious signal that anybody could tell was artificial, but you could also set out a signal that would only be recognized as an intelligent signal by a fairly sophisticated intelligence, because it wouldn't be an obvious signal and it would be almost indistinguishable from the background noise of the universe.
Well, that has technical problems, though. I mean, if you start sending things over interstellar distances, you get dispersion.
Right? You can rebroadcast Snowden, sure.
So, I mean, we already have very sophisticated methods of hiding signals in the background noise. We have that. However, we also have very sophisticated ways of detecting them. So it's a cat and mouse game. You're never going to. The military uses something called, a lot of people do it now, spread spectrum techniques, which where the frequency of the signal is hopping all over the place, and but there are well-known techniques for detecting that and tracking it. It's, in fact, GPS uses that. So, you're not going to, I don't think you'll fool anybody who's got a sophisticated idea. It's just, you still have to transmit something that's got more energy per bit than the background noise. And that's not, that's always detectable by anyone who knows what they're doing.
Let me throw out one more idea. I think that ultimately what's going to be more relevant than sending out mathematics that we think that we share with other conscious beings, I think that we are more likely to understand and be able to communicate our ecology and our place within terrestrial ecology than any abstract mathematical ideas. And by that, I mean that that if we assume that other biospheres are out there and that they've developed the kind of emergent complexity we find in the terrestrial biosphere, you get a lot of different kind of You get some organisms that specialize in predation, some that specialize in fleeing predators, some are omnivores like us, some are,
and 90% of them are parasites, by the way.
and a lot of them are parasites. Some of them are mutualists. Sometimes they're symbiosis. What I'm getting at here is that in another biosphere, the individual organisms will be different. But if biological complexity emerges and you get, competition for niches, that you're going to get a similar structure. You're going to have natural selection. You're going to have specialist organisms, some of which are parasites, some of which are predators, those kind of things. If we could figure out a way to message the universe without messaging in a way that would elude predators and would speak to other species that aren't predators, that would make us perhaps a little more safer if we are going to engage on a large scale MEDI program. Not something I'm advocating. I mean, a MEDI program.
Have you heard about the Voyager Golden Record 2.0?
I haven't. I've heard about it, but I haven't read it in detail, so I don't know.
Well, the guy named John Lomberg, who put together the first, who was the design at that point a young fellow who helped Carl Sagan put together the first Voyager Golden Record. He's now got a Kickstarter going to do a 2.0 version of that, and he among other things, there would be images of animals and plants on Earth. And I don't know exactly, to really represent the cross section, it would be almost all microbes, but I think what they're probably have a disproportionate number of mammals and reptiles.
Charismatic megafauna.
Yeah. Well, and also, creepy ones too. You may have a few crocodiles or pythons in there, but the point is to sort of what they want to do is upload this to the what's called EEPROM, which is a permanent memory, flash memory, maybe on board these satellites that are flying out of the solar system like New Horizons. You put that on there, and then you have they would have images. Now, anybody who's reasonably sophisticated would be able to figure out, okay, this is a matrix of bits, and put it together. And what do you get? Oh, there's an image popping out. And, we can do that. We have the technology to do that now. So I would find, I find that a pretty interesting idea.
It is an interesting idea, but if we want to filter what we're doing so we don't do something dangerous for our home world in terms of a MEDI project, but once again, I'm neither advocating nor not advocating for MEDI. I'm just saying that if we could figure out enough of the evolutionary psychology that's distinctive of predators and what's distinctively different from other forms of life, that we might be able to design a message so that it's, for cognitive reasons, invisible to predators. Of course, since we are predators ourselves, that might give us an insight on the one hand, but on the other hand, we'd be trying to design something that's invisible to us. But if we wanted to safely communicate or send out a message that would be safer than just a broadcast or message to any being that could understand it, obviously intelligent predators who might want to come and wreck your homeworld just for the fun of it would be what you would want to exclude. And if we could do that by understanding the evolutionary psychology of predators or any being that might engage in that kind of behavior, then it might be a little bit safer to send a signal out into the cosmos.
Yeah, I think that's not a bad idea, actually. If you can find some way to encode our understanding of that, which may be the tricky part.
Yes, that would definitely be, the devil would be in the details.
Now, and you've got a Freudenthal. He was more interested in just transmitting fundamental mathematical concepts. I'm sorry, Sam, no semi-simple Lie algebras. It was, basically by repetition, establishing what symbols mean and then beyond that, and then setting up sort of a sequence of symbols, and then from that you could build up to more complex concepts, and so it would be.
I think Paul froze up again. I don't hear him anymore.
Right.
But I was going to say it'd be kind of like the musical dialogue at the end of Close Encounters of the Third Kind, except in mathematics instead of music. And since many people draw parallels between mathematics and music,
well, I know what he's talking about, right? Which is Hans Freudenthal, famous mathematical logician, became interested in this question of communicating to extraterrestrial civilizations later in his life. And what to say about it? I don't know.
He wrote a book called Linkos that was formulated this language in which you could mathematically communicate with some other intelligence.
Right. And what was the useful contribution? I'm not so sure.
Well, he was aiming at absolute generality and mathematical purity that would presumably be shared by any other abstract intellect, insofar as human beings do have the possibility of.
I agree that was his goal. Did he achieve it?
Did he achieve it? I'm
not so sure, but
well, that's why I said I think we might have a better chance if we could figure out in encoding communicating about biology than we would about mathematics. Certainly, mathematics and biology would both be crucial for understanding ourselves and for understanding anything else that we are talking to, because we are biological beings, but we do have this language of mathematics that's not necessarily exhaustively dependent on our biology, separable to some degree.
I definitely agree with that, but with respect to Linkos, what do I think? It seems surprising and it seems very naive to me in a number of regards. Both the linguistics of why extraterrestrial civilizations should expect to have the same linguistic patterns that are detectable in terrestrial civilizations. That aspect of the Linkos work seems completely unfounded to me, and I don't understand why they were confident in that work. With respect to generalizing to extraterrestrial civilizations, yeah, I don't know. I think many of the same skepticisms apply. Like, I basically think it's just irrelevant to modern, quote unquote, discussions of extraterrestrial contact. I don't think
that brings up a very interesting. That brings up the very interesting question of whether mathematics can become outmoded. Because if you're acknowledging that mathematics can become outmoded, or that something has become more or less a dead end, you're acknowledging a significant role for historical contingency in mathematical knowledge.
And I happily acknowledge such a thing.
But the more we acknowledge historical contingency in mathematics, then the more we get the separability of the possibility of a different species of intelligence having a very different conception of mathematics. There's a passage.
I think that's right, but and yeah, the starting point is an important question when it comes to these issues. But I don't know.
Well, we keep working on the problem.
Yeah.
So Paul is still out of the picture, and I don't know when he's going to be coming back. So I don't know what the plan is without the moderator present.
I'm happy to call it a night here. But
Yeah, I see. You're starting to look pretty tired.
yeah.
So
yeah, let's call it a night here. I think these are interesting questions that we've raised. I don't think we've solved any worldwide important problems here tonight, but maybe we've shed some light upon some of them, hopefully. I can think of worse goals in life than that, but we do our best.
we do our best.
Yeah, let's call it a night. And from New York City, good night from Sam.
And from Portland, Oregon, this is Nick Nielsen for the Unseen Podcast. And here's Paul again, so he can say goodnight too.
Yeah, good night.
I'm sorry about that. Technical problems all over the place tonight.
That's all right. We're just signing off, so have a
Yeah, okay. Well, if you're listening, thanks for listening. Check us out at unseenpodcast.com. Thanks to Nick Nielsen.
Thank you, Paul.
I promise we'll do better technically next time, whatever it takes, and which probably means throwing out some of the hardware I just recently bought. And again, unseenpodcast.com. This podcast is issued under the Creative Commons Attribution Share Alike license. And if you have any questions, comments, feel free to join us at our Google Plus forum. And also you can email unseenpodcast@gmail.com. Please feel free to subscribe at your favorite service, whether it's iTunes or whatever your favorite podcast aggregator is. That way you'll get all the updated episodes as soon as they come out. And again, this is August 25th, 2017. And we are signing off. This is Unseen Podcast, episode 77. Music by DJ Spooky. Good night.